What counts as a random variable differs between the frequentist and Bayesian perspectives. In the frequentist view, probability refers to the long-run frequency of a repeatable event across many hypothetical repetitions of the same experiment. In contrast, in the Bayesian view, probability represents a degree of belief that reflects uncertainty about an event or quantity. Because probability is defined differently, frequentist and Bayesian statistics also differ in what they treat as random versus fixed. First, under the frequentist perspective, population parameters, such as the population mean, are treated as fixed constants because they are not associated with a repeatable event. In contrast, under the Bayesian perspective, population parameters are treated as random variables because we are uncertain about the values of the population parameters. Second, under the frequentist perspective, sample data and sample statistics, such as the sample mean, are treated as random variables when we imagine conducting the same study over and over again. The distributions of these statistics across repeated samples are called sampling distributions. Sampling distributions play a central role in frequentist hypothesis testing. Specifically, hypothesis testing relies on the sampling distribution of a test statistic under the assumption that the null hypothesis is true. By contrast, the Bayesian perspective does not rely on hypothesis testing in the frequentist sense. Although Bayesian analysis still uses a probability model for the data, once the data are observed, they are treated as fixed. The observed data are used to update prior beliefs about the parameter through Bayes' theorem. In this sense, the data are viewed as a fixed input, and uncertainty is expressed through the posterior distribution of the parameter. Finally, frequentist and Bayesian approaches differ in how they quantify uncertainty in parameter estimates. The frequentist approach uses confidence intervals. In a confidence interval, the parameter is fixed, while the endpoints of the confidence interval are considered random because they would vary across repeated studies. Therefore, a 95% confidence interval is interpreted as follows. Over many repeated studies, 95% of the constructed intervals would contain the true parameter. In contrast, the Bayesian approach uses credible intervals. Because parameters are treated as random variables in the Bayesian framework, a 95% credible interval is interpreted as follows. Given the observed data, there is a 95% probability that the parameter lies within this specific interval. This interpretation is often considered more intuitive than that of the frequentist confidence interval.